Welcome to the next session. We start the session with the classroom workbook followed by new concept contour integrals. Now let us start question number 33. The residues of a function f of z equal to 1 by z minus 4 into z plus 1 whole cube, or options are given. So this is the function. We need to find residues of this function at 4 as well as minus 1. Here 4 is a pole of order 1 and minus 1 is a pole of order 3. So we need to find both the residues. So let us find residue of f of z at 4 at first. So this is given by limit z tends to 4, z minus 4 into f of z. F of z is this 1 divided by z minus 4 into z plus 1 whole cube. So this and this will get cancelled. Replace z by 4, you will get 1 by 4 plus 1 whole cube, and this is 1 by 125. So one residue is 1 by 125. 1 by 125 is in two different options, B and D. So answer can be either B or D. Either B or D. Now let us find residue at minus 1. So to get the second residue, it must be in the form g of z by z minus z naught whole power m. So this is 1 by z minus 4 divided by z plus 1 whole cube. So therefore this is nothing but g of z by z minus z naught whole power m. G of z by z minus z naught whole power m. Now here m value is 3. So we need to differentiate this with respect to z 2 times. What is g of z? 1 by z minus 4. So g dash of z is minus 1 by z minus 4 whole square. G double dash of z second derivative is 2 by z minus 4 whole cube. So therefore g double dash of, here this is minus 1. So replace this by this. So we get minus 2 by 125. But the residue of f of z at this pole minus 1 is given by g double dash of minus 1 by 2 factorial. So this is minus 2 by 125 divided by 2. So this is minus 1 divided by 125. So one residue is 1 by 125. Second residue is minus 1 by 125. So option B is right answer. 34. The residue of the function f of z equal to 1 divided by z plus 2 whole square into z minus 2 whole square at the pole z equal to 2 is, options are given, minus 1 by 32, minus 1 by 16, 1 by 16, 1 by 32. We need to find the residue at 2. So here 2 is a pole of order 2. 2 is a pole of order 2. So therefore f of must be expressed as g of z by z minus z naught whole power m. So this we can write it as 1 by z plus 2 whole square divided by z minus 2 whole square. Now this is in the form g of z by z minus z naught whole power m. So here g of z is what? 1 by z plus 2 whole square. Here power is 2. So differentiate this with respect to z one time. G dash of z equal to minus 2 by z plus 2 whole cube. So here what is g dash of 2? So minus 2 by 2 plus 2 whole cube. Minus 2 by 64. This is minus 1 by 32. Therefore the residue of f of z at the pole 2 is g dash of 2 divided by 1 factorial. So this is nothing but minus 1 by 32. So option A is right answer. Given x of z equal to z by z minus a whole square. Then the residue of x of z into z power n minus 1 at z equal to a. At z equal to a. So this is my function x of z, z by z minus a whole square, but they were asking residue of this function. So here assume that y of z equal to x of z into z power n minus 1. So therefore x of z is z by z minus a whole square into this is z power n minus 1. So this is given by z power n by z minus a whole square. Now here a is a pole of order 2. A is a pole of order 2. Of course, it is in the form g of z by z minus z naught whole power m. Now, what is my g of z? G of z is z power n. So, here m is 2. So, differentiate this with respect to z only one time. So, the derivative of z is n into z power n minus 1. But here a is the pole, so we need to find g dash of z at a. So g dash of a is n times a power n minus 1. Therefore, the residue of y of z at a is given by g dash of 1a, g dash of a divided by 1 factorial. So this is n times a power n minus 1. So option D is right answer. Just by case 2, because this is my function, they have given to find the residue of x of z into z power n minus 1 at z equal to a. Even a is a pole of x of z and even a is a pole of this new function also. So this we call it as y of z. Y of z is this. Now this becomes z power n by z minus a whole square. It is in the form g of z by z minus a whole power m. But here a is a pole of order 2 because the highest power of z1 by z minus a is 2. So therefore it is in the form g of z by this, but g of z is z power n. So since the power is 2, differentiate g with respect to z only one time. So its derivative is n times z power n minus 1. Therefore the residue of y of z at a is g dash of a by 1 factorial. This is by case 2 of residues. So g dash of a by 1 factorial. This is n times a power n minus 1. Now we discuss a few basic concepts to go for contour integrals. Okay. Next definition, interior point. Suppose we have a circle defined by modulus of z minus a equal to r. This is my circle, modulus of z minus a equal to r. So we denote it as C. C stands for circle, for example. So modulus of z minus a equal to r. Z naught is some complex number. We say that this z naught is interior point of this circle if modulus of z naught minus a is less than or equal to r. So replace z by z naught and simplify this expression modulus of z naught minus a. If it is less than or equal to r, then this z naught will be called as interior point of this circle. See, suppose I have a circle like this. Suppose if z naught is on the circle, or z naught can be inside the circle. So if it lies inside the circle, less than will work. If it lies on the boundary of the circle, then equality works. Suppose if the location of z naught is at this place, then less than will work. If it is on the boundary of the circle, then equality works. So less than for inside and equality on the circle. Either in this case or in this case, this point will be called as interior point of the circle. Let us take a circle. Suppose modulus of z equal to 3. If I take z naught equal to, for example, 2. Now 2 is an interior point of the circle. Even I can take z naught equal to 3. So mod 3 equal to 3. It lies on the circle. Suppose if I take z naught equal to 4. Modulus of 4 greater than 3. So it does not lie inside the circle. It is outside the circle. So therefore there 2 and 3 are the points which are interior points of the circle. So if it is less than or equal, then this is called interior point of the circle. Okay. Write the definition. A complex number Z0, a complex number Z0 is said to be, a complex number Z0 is said to be an interior point of, a complex number Z0 is said to be an interior point of the circle mod Z minus A equal to R, is said to be the interior point of the circle mod Z minus A equal to R if modulus of Z0 minus A less than or equal to R. If modulus of Z0 minus A less than or equal to R. Example, the circle C is defined by like this, mod Z equal to 3. So write these two examples. We can discuss this in the next definition. Even you can write this also, but it does not lie inside the circle. Only these 2 points lie inside the circle. Next definition, exterior point. Exterior points. Exterior points means the points which are lying outside the circle are called exterior points. This is my circle. This is my complex number. We say that this Z0 is exterior point of this circle if a modulus of Z0 minus A is greater than R. Suppose if it locates at this place. So it is lying outside the circle. So therefore outside is denoted by less than. Inside is denoted by less than. If it is greater than, outside. If it is less than, inside. If it is equal, it lies on the boundary of the circle. In both the cases, whether it is less than or equal, it is called interior point. If it is greater than, then this is called an exterior point. Look at this. When you replace Z by 4, mod 4 is for 4 greater than 3. So it is an exterior point of this circle, modulus of Z equal to 3. Write the definition. Exterior point. A complex number Z0, a complex number Z0 is said to be, a complex number Z0 is said to be exterior point of, is said to be exterior point of the circle mod Z minus A equal to R. A point Z0 is said to be exterior point of the circle mod Z minus A equal to R if modulus of Z0 minus A greater than R. If modulus of Z0 minus A greater than R. Write the same example, but at this moment take Z0 equal to 4. It is an exterior point of this circle. This is exterior point. But these two are interior points. Next definition, contour. Now let us see what is a contour. Any closed curve in the complex plane is called a contour. Any closed curve in the complex plane is defined as a contour. Basically, one of the best example of contour is circle. Suppose I have a circle like this, modulus of Z minus 2 equal to 4. So this is one of the contour in the complex plane. See, throughout the contour integrals, we use contour as a circle only. Mostly, not mostly, in almost all cases, the contour will be circle, modulus of Z minus A equal to R. So this is the one of the example of a contour. Write the definition. Any closed curve in the complex plane, any closed curve in the complex plane is called a contour. Any closed curve in the complex plane is called a contour. Example, modulus of Z minus 2 equal to 4. Next concept, contour integration. Contour integration. Suppose we have a complex valued function f of z and c is a contour. Now integrate this complex valued function f of z over some contour, that symbolically we write it like this, integral f of z dz over c. This is the short form representation of a contour integral. So integrating a complex valued function f of z over a contour c is called a contour integration. That mechanism is called contour integration, and this integral is called a contour integral. So what do you mean by contour integration? Integrating a complex valued function f of z over a contour c is called contour integration, and the corresponding integral is called a contour integral, and this is the general structure of a contour integral. Integral f of z dz over c. Note this point. Next concept, contour integration. Integrating a complex valued function f of z, integrating a complex valued function f of z over some contour c, integrating a complex valued function f of z over some contour c, integrating a complex valued function f of z over some contour c is called a contour integration, and the integral is called a contour integral, and the integral is called a contour integral. It is denoted by integral f of z dz over c. It is denoted by integral f of z dz over c. Just write c below the integral, that will be read as integral f of z dz over c. Now our next concept is finding contour integrals using some basic theorems, basic formulae. Okay, very important, almost guarantee question, whether it is GATE or IES. When you are going through complex variables in any competitive examination, the fundamental basic important point is contour integrals. So the next concept is Cauchy's integral formula. Very important, Cauchy's integral formula. Suppose we have a function f of z. Assume that this is analytic at all points. It is analytic at all points inside and on a simple closed curve C. Inside and on a simple closed curve C. Suppose Z0 is an interior point of C. Z0 is an interior point of the closed curve C. So in that case, my contour integral will be like this. Integral f of z by z minus z0 dz over c. This is equivalent to 2 pi I into f of z0. So this is the one of the important model of contour integral. Integral f of z by z minus z0 dz over c. Very standard structure for contour integral. Integral f of z by z minus z0 dz over c. This is a multiple of 2 pi I. 2 pi I times I is a complex number whose square is minus 1. 2 pi I into f of z0. Now this is true only when f of z is analytic at all points inside and on a simple closed curve C, and z0 is an interior point of this curve C. In that case I will get this, and in this case the direction of C is, actually C is a contour, and the direction of the contour is by default anti-clock direction. By default the direction of the contour is anti-clock direction. Mostly contours will be circles. Sometimes circle may move in the anti-clock direction. Sometimes it may move in the clockwise direction. So if it moves along anti-clock direction, the contour integral value will be like this. Basically, this is nothing but f of z naught equal to 1 by 2 pi I into integral f of z by z minus z naught dz over c. So this is one formula and this is another formula. So both are related to Cauchy's contour integrals. So integral f of z by z minus z naught dz is 2 pi I times f of z naught. If z naught is an interior point of this contour C and f of z is analytic at all points inside and on the boundary of simple closure curve C. Of course, the default direction of contour is anticlockwise. Suppose if this point lies outside the circle, in that case the value will be like this. So integral f of z by z minus z naught dz over c equal to 0 if z naught lies outside C. If z naught lies outside C, that means z naught is an exterior point of this circle. This is very important formula. In fact, this is the basic formula for all contour integrals. Very basic. So write these points. Let f of z be a function. Let f of z be a function which is analytic. Let f of z be a function which is analytic at all points inside and let f of z be a function which is analytic at all points inside and on a simple closure curve C. Let f of z be a function which is analytic at all points inside and on a simple closure curve C, and z naught be an interior point of C, and z naught be an interior point of C, an interior point of C. Then integral f of z by z minus z naught dz over C, integral f of z by z minus z naught dz over C equal to 2 pi I times f of z naught. 2 pi I times f of z naught. Highlight this. This implies f of z naught equal to 1 by 2 pi I into integral f of z by z minus z naught dz over C. So actually this formula is coming from this. But in most of sometimes they may ask you contour integral like this. Sometimes they may ask you like this. If they ask you like this, you multiply f of z naught with 2 pi I. If they ask you directly like this, you take only f of z naught. So this and this, highlight these points. If C is moving along anti-clock direction. If C is moving along anti-clock direction. If C is moving along anti-clock direction. Next, note this. Integral f of z by z minus z naught dz over C equal to 0 if z naught lies outside C. Integral f of z by z minus z naught dz equal to 0 if z naught lies outside C. Now let us discuss few examples on simple contour integrals. So let us discuss 2 to 3 examples. Very important concept. This is examples. First one. Suppose I want to calculate integral z square plus 1 by z minus 2 dz over the circle mod z equal to 3. Here this is the circle mod z equal to 3. What is circle C? Mod z equal to 3. Z naught is 2. So replace z by 2, mod 2 equal to 2, this is less than 3. So it is an interior point of this circle. What is my f of z? F of z is numerator function, z square plus 1. Now it is a polynomial expression, so it is analytic at all points. Now z naught is 2, this is f of z, and even 2 lies inside this circle. Therefore, by Cauchy's integral formula, this is 2 pi I into f of z naught. So this is 2 pi I into f of z naught means 2. So this is 2 pi I into replace z by 2. 2 square plus 1. So this is 5. So the final answer is 10 pi I. So only thing is, you need to identify what is f of z and make sure that f of z is analytic at all points inside and on a simple closure curve. This is a circle. In fact, all polynomials are analytic at all points, at all circles. So when the numerator function, when the numerator is a combination of polynomial expressions, constant functions, sin z, cos z, e power z, you need not verify for analyticity of this function. Only thing is, in that case, you check whether z0 belongs to this circle or not. If it lies outside the circle, value is 0. Otherwise, apply the formula 2 pi I times f of z0. So in this case, what is my f of z? Z square plus 1, numerator. And z0 is 2. Circle is this. Modulus of 2 is 2, 2 less than 3. So it is an interior point of this circle. So according to Cauchy's integral formula, this is 2 pi I times f of z0. So z0 means 2. Simplify this, you will get 10 pi I. Note this. Now let us move to example 2. Integral z square plus 1 by z minus 1 into z minus 2 dz over mod z equal to 3. Now unfortunately we have two z0s in the denominator. One z0 is 1, second z0 is 2. See, this is extension of this question. Here numerator is z minus 2, but extra I have taken z minus 1. So here z0s are 1 and 2, both belong to this circle. 1, 2 are interior points of 1, 2 are interior points of the circle mod z equal to 3. So mod 1 is 1, 1 less than 3. Mod 2 equal to 2, 2 less than 3. Both lie inside the circle. But we have discussed Cauchy's integral formula only for single z0. When multiple z0s are there in the denominator, see how many z0s belong to the circle, how many z0s outside the circle. So here unfortunately both z0s belong to this circle. Therefore, we need to go for partial fraction expansion of this. This I can write it as z square plus 1 into this 1 by z minus 1 into z minus 2. I can write it as 1 by z minus 2 minus 1 by z minus 1 dz over mod z equal to 3. So basically this is the partial fraction expansion of 1 by z minus 1 into z minus 2. Anyhow, z square plus 1 is written. Therefore, apply linear property for integrals. This is integral z square plus 1 by z minus 2 dz over mod z equal to 3 minus integral z square plus 1 by z minus 1 dz over mod z equal to 3. Now here z0 is 2, f of z is this. Therefore, this is 2 pi I into f of 2 minus this is 2 pi I into f of 1. That means we have applied Cauchy's integral formula for twice. Once in the case of 2, second time in the case of 1. Now here already f of 2 is 5. This is. So therefore this is 10 pi I minus f of 1 is 2. So this is 4 pi I. So the final result is 6 pi I. This is one important model. When many z0s are there in the denominator, see how many points lie inside and how many lie outside. When all points lie inside, go for partial fraction expansion. In future sessions, I will tell you how to get these integrals even without going for partial fraction expansion also. Okay. For the time being, you try to understand this. So I went for partial fraction expansion of 1 by z minus 1 into z minus 2. I got this. Now between two functions, we have a minus symbol. So I can go for linear property for integrals. So I have applied in the Cauchy's integral formula for 2 and I applied Cauchy's integral formula for 1. So that means indirectly we have applied Cauchy's integral formula twice. Once in case of 1 and once in case of 2. So finally we were getting 6 pi I. Note the second example. Example 3. Suppose I want integral z square plus 1 by z minus 2 into z minus 5 dz over mod z equal to 3. Here we have two z0s. F of z is z square plus 1 only. F of z is z square plus 1. Now here 2 and this is 5. But 2 lie inside the circle, 5 lie outside the circle. 2 lies inside the circle, 5 lies outside the circle. So because of that, slightly I will do some changes for f of z. Then I will do like one thing. So I will write here 2 lies inside mod z equal to 3. 5 lies outside mod z equal to 3. So since this point is lying outside the circle, this z minus 5 can be given to numerator directly. Therefore, this integral can be written as z square plus 1 by z minus 5 whole divided by z minus 2 dz over mod z equal to 3. Now this is f of z and this 2 is z naught value. But what is the drawback of this f of z? You may ask me, what is the drawback of this f of z 5? So the f of z is z square plus 1 by z minus 5. But it is analytic at all points except at 5. It has a drawback, but 5 is not a member of this circle. Therefore, it is analytic at all points inside and on the boundary of this circle. Therefore, you can apply Cauchy's integral formula. Therefore, this becomes 2 pi I into f of z naught. So therefore this is 2 pi I into f of z naught is 2. So therefore 2 pi I into 2 square plus 1 5 divided by 2 minus 5 3. So the answer is minus 10 pi I divided by 3. So when multiple z naughts are there, if all z naughts belong to circle, go for partial fraction expansion like this. If one point lie inside the circle, one point lies outside the circle, you can do manipulation like this. Even if you go for partial fraction expansion also, you will get the same expression. But to minimize the time, better to solve this. Okay. So the answer is minus 10 pi by 3. Did you understand this? Here 2 lies inside the circle, 5 lies outside the circle. So z minus 5 can be given to numerator so that it has a drawback 5. But 5 is a drawback, but that is not in mod z equal to 3. So that's why I can distribute z minus 5 to the numerator so that my f of z becomes z square plus 1 by z minus 5. So according to integral formula, this becomes 2 pi I into f of z naught. So f of z is z square plus 1 by z minus 5. Z naught is 2. So I will get minus 10 pi divided by 3. Note this. Suppose we have integral z square plus 1 by z minus 4 into suppose z plus 5 dz over mod z equal to 3. Here what are my points? 4 comma minus 5. Mod 4 is 4, 4 greater than 3. Modulus of minus 5 is 5, 5 greater than 3. So both 4 comma minus 5 lie outside the circle mod z equal to 3. So multiple z naughts are there, but both z naughts lie outside the circle. Therefore, this integral z square plus 1 by z minus 4 into z plus 5 dz over c. C means mod z equal to 3 is 0. So when you look at last 3 examples, do one strategy. When both z naughts belong to circle, go for partial fraction expansion. Apply Cauchy's integral formula twice. When one lies inside, one lies outside, distribute the point which is lying outside to the numerator and apply integral formula once. If all points lie outside the circle, the value becomes 0. In this case, 4 and minus 5 lie outside the circle, so its integral is 0. Write this as example 4.